Hi, my name is Ken, and I'm excited to present our paper, How Do Analysts Understand and Verify AI-Assisted Data Analyses, which was an internship project completed last summer at Microsoft Research. Improved capabilities of large language models have led to a range of promising data analysis assistants such as GitHub Copilot, ChatGPT, Code Interpreter, and Copilot for Excel, which can all assist analysts in automating and executing their analyses. These assistants, given natural language instruction, can handle specifying and performing the data operations. However, given the flexibility of natural language, this presents its own challenges. To see this, let's look at a motivating example. Jane and Alex are data analysts at an e-commerce platform and want to find out how many distinct products bought in November were later returned. Jane does her analysis in the traditional way, using a spreadsheet, and ultimately arrives at an answer of 2. Alex uses OpenAI's Code Interpreter assistant and writes the prompt, how many items purchased within the month of November were returned to the seller? In this case, the AI assistant does the calculations and returns a value of 5. But this is different from Jane's answer of 2, and upon closer inspection, Alex realizes the AI calculated number of units returned rather than the number of unique products returned. Alex cannot simply trust the AI's response, as AI-written analyses may contain hard-to-detect errors. The paradigm now shifts from analysts having to formulate the exact transformations and operations in analysis to understanding and verifying AI-assisted analyses. In this work, we aim to study how analysts understand and verify AI-assisted analyses. To do so, we conduct a user study with data workers in which they understand and verify real errors made by today's data analysis assistants. First, to facilitate analysts' natural sense-making workflows, we chose to purpose-build the design probe and provide additional data artifacts based on recommendations from prior work. For detailing the procedure, our probe provides the code comments, and natural language explanations that is provided in existing assistants. As well, there are buttons interleaved in the procedure that open up the respective data artifacts, that is, the original, intermediate, and any result data tables. For the data, we chose familiar and approachable supporting artifacts so as to mitigate the challenges tied to learning and interpreting customized visual elements. We include interactive data tables with basic filter, search, and sort functionality. These data tables also have a corresponding data visualization summary containing a histogram for each data field and summary statistics. For the verification tasks in our study, we decided to prepare them beforehand and select the tasks ourselves. This enabled us to mitigate variability associated with generative AI and dataset complexity. Likewise, we focused on one turn of the human-AI interaction so as to remove the difficulty in crafting prompts. Using an existing dataset containing data scientists' written prompts across 70 distinct datasets, we ran GPT-4 against the prompts and manually inspected the responses to find errors. We then ran a subset of these on Code Interpreter for realistic outputs. In total, we selected 10 main tasks, 8 of which contain errors. For each of the tasks, we prepared the following task material: the natural language query, or prompt, and a more comprehensive analytical description for participants to remove any ambiguities. The dataset, which contains a more detailed dataset and column description, Code Interpreter's unmodified response, and additional intermediate data tables and visualizations. Moving on to our study, we sought to ask 2 main questions. What patterns of behaviors do analysts follow in a verification workflow? And what artifacts do analysts use, and for what purposes? We recruited 22 data workers across different roles, such as program managers, software engineers, and data scientists, for a 1-hour online study. In the hour's time, each participant did a subset of the 10 tasks. For the task instructions, participants were asked to verify the work of an intern who used an AI assistant to perform the given analysis goal. This was done such that participants do not focus on the quality of the prompt, but on the AI-generated output in response to the prompt. Across all participants, we observed 52 task verification workflows, 39 of which involved errors. In synthesizing our observations, we rewatched all participant workflows and organized our observations into 2 high-level behaviors within a verification workflow: procedure-oriented behaviors, that is, what does the AI do, and data-oriented behaviors, that is, does the data make sense? Participants may have used both procedure and data artifacts as part of a given behavior, but what we captured was their intent behind their actions. Now, jumping into our results, we observed participants initially gravitated towards procedure-oriented behaviors, and shifted towards data-oriented behaviors after noticing an issue. In addition, these behaviors serve different specific goals for the participants. Some participants adopted procedure-oriented behaviors to get a high-level understanding of the data steps. Others focus on the procedure to confirm details in the data operations. Meanwhile, participants adopted data-oriented behaviors to better understand the structure of and relationships in the data. With respect to the artifacts used, we notice all artifacts, both data and procedure artifacts, were vital to support verification behaviors. Likewise, there was no obvious preference for any specific artifact. We also noticed specific things analysts focused on when using these artifacts. This included using the data artifacts to gain an expectation of what they might expect and identifying issues regarding the AI's understanding of the semantics of the data. Participants also used procedure artifacts to ensure the AI's approach matched how they would approach the problem, track the provenance of data across operations, and find discrepancies in the procedure. Overall, there was a lot of shifting between procedure and data artifacts to support these different verification behaviors. Given our study findings, we now discuss implications for both data analysts and system designers. First, with respect to data analysts, we find that data literacy is still a vital skill. While knowledge in a specific programming language was not necessary, we found that knowledge and experience in data analysis was often indispensable for grasping AI-generated analyses. This mirrors the requirement for computational thinking skills when working with AI-based code assistants. We recommend analysts to know common data operations and know the strategies for quick data validations, such as sanity checks on what the shape of the data should look like or what an aggregate of a column should look like. For system designers, it is important to fluidly connect the procedure and data artifacts at various levels of granularity. Connecting the artifacts makes sense, as the data and code are intimately tied to each other. The different levels of granularity is necessary to support analyst verification at different levels of abstraction, from quick glances and checks to detailed inspection of the procedure or data. An example to support this could be that when an analyst selects the text of a column name or cell value in the procedure, the tool can quickly highlight the corresponding data. Meanwhile, if the analyst selects a code snippet containing multiple data operations, the tool can highlight the corresponding data differences between the operations. Next, it is important for the AI to communicate its assumptions and interpretations of the data. We noticed participants had an easier time identifying mistakes when the AI stated its interpretation of a certain column. Therefore, the AI should communicate things like what it thinks each column means and how the data relates semantically to the input, prompt, or query. Finally, there is an opportunity to incorporate AI guidance into verification workflows. Given the rise of AI agents, we can leverage LLM-powered agents to generate test cases and perform self-reflection on potentially erroneous or doubtful assumptions. In addition, from the interface side, we can highlight the AI response with visual warnings, taking inspiration from prior work on writing interfaces with LLMs. Taking a step back, the rise of LLM-based agents with memory, reasoning, reflection, and code writing capabilities offer exciting avenues for human-AI collaboration in data science. In this work, we conduct the first user study to explore analysis verification practices in the new paradigm in which AI assistants can specify and perform the operations. From observing data workers across various backgrounds at a large technology company, we see that literacy is the utmost important skill. For system designers and HCI researchers, it is important for these data analysis assistants to provide both procedure and data artifacts that are in sync with each other and offer different granularities of verification. Finally, with this understanding of verification workflows, there are great opportunities to incorporate AI guidance. I hope you learned a lot, and thank you for listening.